Welcome to Study Loop.
All right, so problem number 55 states, so part A, for the finite potential well of figure 40.13, what relationships among the constants A and B of equation 40.38 and C and D of equation 40.40 are obtained by applying the boundary conditions that psi must be continuous at x equals 0 and x equals L. So let's start here. I'm going to draw the potential well given in figure 40.13. It's a well that looks like this. Actually, give myself more room. All right, so this is 0. This is L. This is our x-axis. This is our u of x-axis. This is u0. And so for equation 40.38 and 40.40, so 40.38 gives the wave functions for psi of x for x is equal to 0 inside the well is equal to a cosine square root of 2me over h bar x plus b sine square root of 2me over h bar x for x less than 0, which is less than L. And then psi of x is equal to CE to the kappa x plus DE to the minus kappa x for x is less than 0 and x is greater than L. So outside of the box, outside of the well, I should say, this is our potential. This is our potential, and inside the well, this is our wave function. Sorry, not potential. So to keep the boundary conditions that the wave function cannot approach infinity, so one of the primary wave things to constrain your wave functions, a boundary condition, is that it cannot approach infinity. So in order to do that, we can make the statement that psi of x is equal to CE to the kappa x for x is less than 0, because that will keep this negative and it won't blow up. And psi of x is equal to DE to the minus kappa x for x is greater than 0. So again, it'll stay minus and it won't blow up. So you just you'll get an exponential decay outside of the box. And then inside the box, you have some oscillatory function. So D is equal to 0, C is equal to 0. So now if we let K equal the square root of 2me over h bar, then the boundary condition, for part A, where it asks what are the relationships, we use the boundary condition that psi of x must be continuous at the boundaries at x equals 0 and at x equals L. So for that, we will say at x equals 0, so at x equals 0, we have a cosine of 0 plus b sine of 0 is equal to, so at x equals 0, so this is going to be this boundary, so we're using this wave function here, the c, so where d is equal to 0, CE to the 0. So that gives us the boundary conditions A is equal to C, because sine of 0 is 0, cosine of 0 is 1, e to the 0 is 1, so A is equal to C. And then, so like I said, since D is equal to 0 for x is less than 0. So now we'll move at x equals L. At x equals L, we have A cosine KL plus B sine KL is equal to D e to the minus kappa L. So this K and this kappa are not the same. So I'll try to make sure I try to write them differently so you can see that. So now that's the relationship between our coefficients, A and B and C and D of equation 40. So now for part B, we're looking at the conditions that the derivative must be continuous at the boundaries as well. So we'll say for part B, at x equals 0, d psi dx is equal to kb cosine of 0 minus ka sine of 0 is equal to kappa d, kappa c e to the kappa times 0. There's k's in here. So evaluating that, cosine of 0 is 1, sine of 0 is 0, so we get the boundary conditions of kb is equal to kappa c. And then now at x equals L, we have the derivatives give kb cosine of KL minus Ka sine of KL equals minus kappa dE to the minus kappa L. And again, keeping in mind that kappa and K are not necessarily the same. So doing all this allows, basically the point of this is it allows you now, we have these different equations for A, B, and D, and C, and now we can use these equations to express all of our variables, all of our constants by a single normalization constant, usually A. So we solve everything in terms of one of these and then apply it. So that's what the relationships and what's obtained by applying these boundary conditions.